everyone. In this lesson, we're going to go over another method of calculating enthalpy. We've already done calorimetry, so this is our next method. And we move on to Hess's law. All right, I'd like to begin by referring to a practical example here that has a bit of overlap with physics. Okay, so the question is, if you're considering walking up some stairs or taking an elevator, so you both begin, or you begin at different instances in the lobby of a building or in a school atrium, you go up to the third floor or up to the top floor somewhere. How much potential energy did you gain if you took the stairs compared to the elevator? And think about it, it's actually the same. Yes, you spent perhaps more energy going up the steps compared to using the elevator, but for a chemical mechanism, it will be the same, and we are going to consider different changes in enthalpies along the way, so the path does matter, but essentially different paths will lead to the same result. Okay, and that same result is a result of the sum of all of the individual reactions that are involved in an overall reaction. Right? We know after finishing our organic chemistry unit that we have reactions don't tend to be more than, well, they don't tend to be just one-step reaction. They tend to be more than that, and those are called reaction mechanisms. Each of those individual reactions, if you add up their enthalpies, their individual enthalpies, they give you the overall enthalpy of the overall reaction. And here's an example. N2 and O2 react, and they will give you, at the very end, after a two-step reaction, they will give you a product, NO2, right? So reactants are here, products are over here. Now, this is actually a two-step reaction. First step involves an endothermic reaction where you gain 180 kilojoules to get these products. Right? These react, and when they do, they expel, so exothermic, in a second reaction, that much energy. All you then do is you add these two, right? Add these two, 180 kilojoules, and you add negative 112, it's really subtracting, and you get the enthalpy of the overall reaction, which is 68 kilojoules. Look at 68 kilojoules. Right, so all of those steps ended up leading you to the same place as if you went straight there, right? Just like that elevator and stairs example. Okay. So adding up all the individual reactions sound pretty simple, and it really isn't too difficult. It does require practice. You will need to do something similar to what you learn in grade 10, solving linear equations. So if you're fond of math, this is for you. Okay, these are steps to solve a Hess's law question. I don't usually go read over this, as you know, because it's better to see in context, but I do want to summarize these two. So you will end up needing to change signs of an enthalpy value or change the positions of the reactants. That means reactants will become products and products will become reactants. And when you do that, you need to also change the sign. Again, it doesn't make much sense right now, but when we get to an example, you'll see. Also, if you have to change the magnitude, so you have to change the coefficient of a reactant or product, so you're going to multiply by a certain value, by 2, by 3, by whatever it may be, you also have to multiply the enthalpy of that reaction by 2 or 3. Okay, doesn't make much sense, but it will when we do examples. The first one isn't a great one, it's just showing you the basic idea behind Hess's law. So these two reactions make up this final reaction. Now when we add them up, you'll notice that we're going to cancel out all of the substances that appear as both reactants and products. Now they have to be exactly the same. So notice NO, 2NO are canceled out, 2NO are canceled out here. There are two oxygens, one here, you add them together, you get two oxygens. So the final reaction is this, and these are the individual steps. You then also add, just like you did your reactions, you also add enthalpies, and you get 68 kilojoules as your as your enthalpy of the reaction. Okay, to a real example. Example 1. So it's important to do two things. Highlight, look at your end goal. This is the reaction you need. You need the enthalpy of this reaction. Here are the steps to get to those reactions, to that reaction. Let's start analyzing. So you have carbon and oxygen on the reactant side. Carbon and oxygen in this one equation is on this one reaction is on the reactant side. That means you don't want to flip this. They have to stay exactly where they are. But now look at CO2. CO2 isn't in the target reaction. You have to somehow get rid of this CO2. That can't be here. Somehow you're going to have to get rid of it. Okay. Now your reactants on this side, carbon monoxide, shouldn't be here. It should be on the other side. See, CO is on the other side. So we're going to have to flip around this reaction. Okay, you've analyzed it. You now begin to understand what you might need to do. Let's go ahead and do the math, or do work on the problem. So I'm going to rewrite question 1, rather reaction 1. Okay, and because I haven't changed that at all, it has the same enthalpy value. Okay, reaction 2, I am going to treat a bit differently. Reaction 2, I'm going to multiply that by -1. That means two things. Reactants and products get reversed, and this sign, or this enthalpy value, is also multiplied by -1. Okay, so CO2 okay, that sign is positive. Okay, let's see if this works. So this gave us a new equation. We're going to cancel out CO2, right? They appear on both sides. O2 appears on both sides, but look, it doesn't appear exactly the same, but we should still cancel them out. We have half an oxygen here. We have a full oxygen there. Well, 1 minus a half is a half, right? So let's write this down. We're adding all of this up. So carbon, right, that 1 minus a half became a half an oxygen. Oh, this is solid, it looks like gas. Okay. And what we're left with in our product side is carbon monoxide, which is exactly what our target reaction looks like. We do the same. We add our enthalpies here, and we end up with -110 kilojoules, and that is our final answer. Okay, next. Okay, so here it's asking us to figure out the enthalpy of this target reaction using these two. Now these aren't labeled, let's label them. So 1, 2. Okay, now let's analyze. We always have to analyze. So we have nitrogen and oxygen on the reactant side. Okay, nitrogen and oxygen on the reactant side. Okay, we don't want to flip this, so it looks like similar to the previous question. We have NO on the product side. Look, we want to get rid of that NO2 there. It doesn't seem like it should be there. Nowhere does it appear in your target reaction. Look here, we have NO on the left-hand side. We need that on the right-hand side to match a target reaction, so we're probably going to have to flip this, right? Which would work great because if we do, NO2 goes onto the reactant side and we can cancel out those two NO2s and we're good. So let's start working on this. Reaction 1, I'm going to write out exactly as is. Nothing happened to the reaction itself, so I'm going to just rewrite that enthalpy. Okay, then number 2, I'm going to multiply that by 1, right? We talked about why that should be the case, our first step. So that flips the reaction. Right? And our enthalpy has to be switched, so positive 56 kilojoules. Okay, now let's start canceling. All right, so NO2 gone. That's perfect. Okay, what we're left with now is our third equation, which is half N2. Oh, I stopped writing looks like I stopped writing the states, but you should. We'll continue this way though, just to save some space here. And we get something similar here. We have 1 oxygen on the left here and half on the right. So this is gone. This becomes a half. So half O2, and there we go, writing that down. All right, well, we'll try to be consistent next time. And what we're left with is then NO on the product side. Now this looks similar to our target reaction, but it's not quite. Let's continue what we did, that we've added these two reactions. We should add the enthalpies, and we get an enthalpy value for equation number 3 of 90 kilojoules. We add them together. Okay, we're not done though. We need to take equation number 3, and what do you think we need to do to it? This has to become that. Hopefully you're saying, or thinking right now, multiply by 2. Take reaction 3, multiply by 2. And we get N2, O2, and 2NO. We also have to do the same thing to our enthalpy value, which means enthalpy is then 90 times 2 is 180 kilojoules, and that is our final answer. We're done. Okay, one more. I believe this is posted online. Just some, my thought process behind this was, and the student I had came up with one himself, and it's really quite similar, but read this through yourself, see if you can come up with your own method. I used to have a physics teacher that would say, had the saying, once there's more than one way to skin a cat. I think I've used that before when we talked about organic chemistry and organic synthesis reactions. There's different ways to do these types of questions. So if I'm doing it one way, you come up with a different way, that you likely will, and that as long as you get the final enthalpy correct, you're fine. Okay, so I'm probably going to need a couple of slides here, but we'll start with this. So this is our target reaction, right? We need to come up with enthalpy here, right? Switch. Okay, let's analyze first reaction. Okay, this we know has to be switched. We have to flip that, right? Because this should be on the other side. What else? Also, CO2 doesn't appear in our target reaction at all. Let's put a box around our target reaction. Okay, oxygen. Interesting. Oxygen does appear correct, but we do have to flip this though. Right? It'll work out. You'll see. There's also some funny looking fraction here. A 9/2. Okay, we got to work with that. Another reaction. Carbon is where it should be. Oxygen, it is where it should be. CO2, we have to figure out how to get rid of that CO2 because that doesn't appear in our target reaction. Finally, hydrogen appears as a reactant, so that should stay there. Oxygen appears as a reactant, that should also stay there. And water, well, we got to get rid of water. Water isn't in our target reaction. Okay, what do we do? Like I say, there's many ways to approach this. Now, what we're going to try to do, let's look at our coefficients. Reaction 1, let's label this. Yes, we should label this 1, 2, 3. Okay, let's get rid of that 2. Don't like how that 2 looks. Also, the coefficient has to be here has to be a 2. So let's do the 2. But I'm also thinking now, why don't we multiply that by -2? That would solve 2 problems, right? It would flip it and it would give it the right coefficient while getting rid of this fraction. So it'll solve a few things. All right, let's do that. So 1 times -2. Now that becomes, remember, we're flipping and multiplying at the same time. So 8H2O plus 6CO2. Okay, enthalpy is now positive 2008. Okay, that should be kilojoules. Okay. Don't forget enthalpy, we change the sign and we multiply by 2. Now, reaction number 2. We have to multiply this by a certain value. Okay, look at the carbon here. Everything's where it should be except for CO2. This will end up canceling out. You'll see that just like hydrogens work out about on their own when you're balancing a reaction, the same thing tends to happen with Hess's law. So don't worry, don't try to solve everything all at once. It will end up usually solving itself without much trouble. Carbon needs to be 6 carbons. Let's multiply that by 6 then, right? 2 times 6. and we get 6 CO2 plus 6 O2 produce 6 CO2, and our enthalpy value is just multiplied by 6, and that's going to be negative 2364 kilojoules. Right, reaction 3. Reaction 3, let's look at our coefficients. Look, this is an 8, that's a 1, let's multiply that by 8. Right, so 8 right, that's a 4 because it was originally a half. Our enthalpy is going to be different. Multiplied by 8, we get negative 2,288, also kilojoules. Okay, let's add this up. All right, let's see what cancels out. Well, look, fortunately, the waters are gone, right? 8 waters on both sides. Now, what else did we not need? We didn't need CO2. Let's see if we can cancel out 6 CO2 here. And that should cancel out here. Yes, right here. I think I didn't write something here. Let's go back. This is reaction 2, should be 6 carbons, not 6 CO2. Then that followed by oxygen and CO2. Perfect. Okay, you probably saw me doing that as it was occurring. Okay, this is 6 carbons, not 6 CO2. Okay, so 6 carbons. Okay, I was about to cancel that, and that shouldn't be. Okay, so 6 CO2, 6 CO2. Now, what else appears on both sides? All right, well, we have 9 oxygens here. We have 6 and 4 here, right? So we can get rid of this 9O2 because we have actually 10 O2. So we'll get rid of those 6 entirely, and we're left with 3 to subtract from here. So we don't get rid of all 4. We still have 1 oxygen left. And I think that's all we have to get rid of. Now, if we add everything up, we get 6 carbons, right? 6 solid carbons. We get 8, right? We're just rewriting, so 8 H2 here. Then that will be followed by our 1 oxygen that was left over. Okay, that produces what's left over in your product is only one thing, 2C3H7OH, and look, that matches our target reaction. That means all we have to do is add our final value here, and I don't have that ready, but let's go ahead and pull up a calculator, and we can say 2008 plus negative 2364 minus 2288, 26, negative 2644 as our final answer. A bit messy, but minus 2,644 kilojoules is our final answer. Okay, that's your home fun. Give it some practice. There are also some worksheets posted. There's some great questions here, though. Give that a try and send over any questions. Until next time.